So I actually realized, especially for folks who are not necessarily engaged in the FIDO community, I realized we've probably been throwing around a couple terms that might not be known. LFN or LF networking, a number of people have said that, and if you're not involved in those projects, you might not know that term. LF networking is an entity that we launched at the beginning of this year, which brought together several of the existing networking-focused open source projects in the Linux Foundation. So the projects that are a part of that are FIDO, Open Daylight, SDN controller, ONAP, which is sort of management and orchestration, OSS, sort of a BSS, basically back office software for the telecom providers, and OPNFV, which does sort of systems integration and testing kind of for the end-to-end platform, as well as two projects called Panda and SNAS, which are analytics platforms for networking. So that is a term that we've been using, so in case some of you were confused sort of about that, and they're all Linux Foundation open source projects. The other term that you maybe have heard us talking about is XCI, and that is our cross-community CI/CD initiative across a number of these projects, plus OpenStack with the Ansible team, and we are currently integrating with the CNCF OpenCI project as well. So I just realized that those are some terms that we didn't necessarily define, and if you are new to the community, you might have been confused by them. We live them every day, so sometimes we forget to define them. So I just wanted to make sure folks knew that. So next up, we have got Florin, who is a software engineer at Cisco and a very active contributor and committer within FIDO, and he's going to talk about the VPP Host Stack. So take it away.
Thank you very much. And also very jet lagged. So again, for those of you who don't know me, my name is Florin Coras. I'm a Cisco software engineer, one of VPP's committers, an overall community contributor. And those of you who've been from the beginning of the project, you may know me from my work on the overlay network engine or one Lisp, but in recent times, I've been spending most of my energy on VPP's host stack, and this is actually the subject of today's talk. Now, this is joint effort. It's done together with a number of colleagues of mine, and we've been executing this on two main tracks. One of them, Dave Barrick, our fearless leader, and myself, we've been working on writing the stack and integrating it within VPP. And on the other one, Keith Burns, Dave Wallace, they've been working on a wrapper library, which is meant to provide easier to consume APIs compared to the raw APIs the stack offers. This presentation is focused on the former, meaning on the transparent session layers of the stack. I'll try to give you some pointers to the API as well as we go along, but not too many. So for the benefit of those of you who are not familiar with the subject at hand, I'll just give you a very, very brief introduction of why this actually exists. So as you all very well know, VPP at its core is just user space, highly optimized, very efficient, back and forward there, with a feature set that's somewhat traditional to that of traditional networking equipment, but with the one very important difference that it runs really fast, runs really well on commodity hardware. And as you've seen already today, that means x86 Intel CPUs. Recently, we're doing that with ARM. Although there's a big start in the margin there, we're not really constrained to this, but this is what we're seeing today. But coming back to performance, although Maciek did not insist too much in today's slide on that, but if you've been keeping a very close eye to the project, you know that VPP can forward something like over 1 terabit per second with millions of routes in the fib. And in other words, it's blazing fast. However, we should not forget that the focus is not entirely performance. We hopefully, as we move forward, VPP will, VPP in particular, let's say, and FIDO in general, will better integrate or seamlessly integrate into the existing SDN stacks, or in the future stacks. And as we evolve, hopefully it will become the foundation of future cloud native services. And dare I say that perhaps these two last items are the reason why the code has actually been open sourced. So having gone over this, it still doesn't provide you too much context. Why did we decide to implement yet another, what was it, Ray, 12 user space host stack? Why did we implement 13? I actually I never counted. So, and this is the point where I could start ranting about the Linux kernel, where I could say that there's some issues with how with the fact that it does serialized processing, not very multi-core friendly, scalar packet processing design that disregards locality. So that's maybe not the most efficient approach, or even the fact that it's not very flexible. So you can modify the kernel. That's not an issue, but eventually the problem is going to be upstreaming those changes and getting those changes back in whatever you want to use. But no, the reasons are actually the reason actually is the fact that we've observed that VPP in combination with the Linux kernel, when deployed, when doing container networking, does not work very well. It's actually pretty inefficient. And if you remember from the previous slide, this goes against one of our core beliefs that we want VPP to be a foundation for future cloud-native services. So to better understand this problem, let's take a very, very simple example here. So say you have two processes, PID 1234, wanting to talk to PID 4321 here. And as they typically do, they link against glibc and they use sockets to exchange some data. Now, to do that, the sender would need to make a syscall, let's say send, push data from user space into the kernel space, into some form of a FIFO. This goes into TCP layer, IP. Eventually, you have network devices or bridging there, and then you go back up the stack. And eventually, at the end of another syscall, recv, you get the data into the other process. But this is not actually, this is quite heavy, but this is not the problem. The problem is when you add VPP to the whole architecture, you suddenly not need only to cross the stack twice, but now you have to pay the additional cost of ingesting that data from the user space, from the user space into the kernel, into VPP finally, with something like AF packet or TAP, and then re-inject that data into the kernel to be consumed in the user space yet again. So that's pretty inefficient, I'd say. And even though we have now technologies or solutions that work very well, like TAP v2, and kudos here to Damian for making that blazing fast, at an architectural level, this doesn't look very good. Perhaps we could do a bit better. So that's what got us thinking about building another host stack, and the I believe not very original solution that we came up with was, hey, why not use VPP as an introductory mechanism between the two processes, and then build some shared memory infrastructure for the two of them to exchange data. So like say our own FIFO implementation, shared memory FIFO implementations. And only in the situation when this data needs to be communicated off the box, so only when we need an actual network support, only then use the host stack. Now the problem at that time was we didn't have a host stack in VPP, and that's what we set to do then. And from a very, very high level perspective, you could see the host stack as being composed of, let's say, 4 major blocks. 3 of them are part of VPP. 1 is actually at the border between the application and VPP. And let's go over them one by one and talk about them in a bit of detail. So first of all, the session layer, or that's what we call it. It's just a shim layer between the application and the transport layer that sits underneath. Because of that, because of its position, is the one that maintains per application state. So it knows where to find the application. It knows how to receive notifications from the application and how to push notification. It typically pushes and receives those notifications per sessions, being the session layer, and session being the unit of communication here. And because of that, session layer is also the one that allocates and manages sessions. It has to also do that with segments, shared memory segments, and FIFOs. We'll get in a second to those. And because it's the one that allocates everything, it's the one that knows how to find everything. So it has session lookup tables. It maintains session lookup tables. In case of VPP, these are 5-tuple based. In addition to that, it offers options for how the applications can interact with the networking. It can control, or let's say police, the way applications interact with the networking. And at this time, we have two possible solutions. One of them are namespaces. And by that, through those, the session layer can control the sort of network resources, underlying network resources like interfaces and IPs that applications have access to. And then we also have within the session lookup tables something that we call a form of ACL, something that we call session rules, via which we can filter. We can do at session layer ingress and egress connection filtering. And we'll go over this last two in greater detail towards the end of the presentation. And
I'm sorry, stupid question here. As a user of TCP, I'm not aware of sessions. What's a session?
It's a socket, if you will. It's the socket layer in the kernel. Now, makes it easier?
Thank you, yes.
So it's pretty much, it's a bit more, I would say, because of the sort of features that we have. But conceptually, if you are to map it to the Linux kernel, it will be the socket layer. And I didn't mention, please feel free to interrupt me at any time. We support pluggable. The session layer is also built in such a way that it supports multiple transport layers. So it's not built for only one transport, so not only for TCP as shown here. And it exposes a raw, well, both of them are raw, the binary API, a binary API, and a native C API for either external applications that want to use the stack and applications that reside within VPP, or something that we call built-in applications. The other component is the shared memory infrastructure that we've built for allocating shared memory FIFOs. Well, this has changed. I've done this presentation, I think, once before at the previous KubeCon. There's big news here. We've changed a bit the way this works. So previously, we only supported shared memory segments that had file backings. And because of that, basically we use devshum as a rendezvous point between VPP and external applications. So both of them have access to devshum. We just exchange file names, and because of that, the two of them can map the same segments. Now, this is not very secure, especially if somebody gets to peek into your devshum and can peek into all the communications that happen through VPP. Because of that, recently, the binary API in VPP has support for two types of transports, shared memory and socket. So what we're doing now, we're leveraging the socket API to do to exchange file descriptors over the socket, memfd file descriptors. So now the application and VPP can exchange those file descriptors securely and map memory mapped shared memory segments, I guess would be the whole name. So that's a big feature. So now we have really secure shared memory segments negotiated between VPP and the applications. Within those segments, we allocate shared memory FIFOs, and these are fixed position and fixed size. Because of that, we can now, within the whole code, start passing pointers around. We don't have to pass any, we don't have to be very careful with that. The service they offer from an external perspective is lock freeze enqueues and dequeues. With the one constraint that because on a FIFO you may have a reader and a writer at both ends of the FIFO, we need to do atomic increments of the size of the FIFO. Otherwise, well, it won't work too well. They also offer some special functions for reliable transports. So for things like TCP, we can do, they have the option of just reading data without removing it from the FIFO, because maybe the transport will want to reread it for retransmissions, and only once the acknowledgement is received, only that is removed. And they also understand out of order and queues. So if TCP sends data out of order, it knows how to join it together. The other thing is, the other component, the third one, is the transport layer. Well, you can do only so much with a team of 2. So we decided to implement the most commonly used transport protocol that happens to be TCP. This is a clean slate TCP implementation tailored for VPP, let's say. So that's why we've done it from scratch. To the best of our knowledge, this is a complete state machine implementation with all the typical properties of a TCP layer. That is, it knows how to do connection management, flow control, congestion control. So, we have our own timers implementation, which is quite scalable because we wanted to do 10 million connections without issues, and we managed to do that even with 2 worker threads in VPP. We use those timers for timer-based retransmits. We also support fast retransmission, and if the TCP peer supports selective X, we can do SAC-based fast recovery. If not, we can do new Reno-based recovery. As you probably have figured out already, we only support right now new Reno congestion control. We don't do cubic. Nonetheless, cubic is an RFC hasn't been an RFC for very long. In terms of hardware support, we do. Go ahead. Yes, yes. There's only 2 hands and 24 hours. In terms of hardware support, we do check some offloading. We do not do any sort of segmentation offloading, either TSO or GSO. Reasons have to do basically with the fact that we need to change the whole of VPP, not only the stack. And there's ongoing efforts in this direction. Hopefully that will change soon. And we don't do anything on receive side either. So we don't have support for all our EO and GRO. And we've tested the compatibility with the Linux TCP stack using a protocol tester from IWL. And again, let me underline the fact that we support multiple transports. This wants to be a generic host stack that has multiple transports. We support right now SCTP. Kudos to Marco. He will do a presentation about this a bit later. Actually, the next one, I think. We support finally UDP in connectionless, not connected mode, and with datagram delivery, so not stream delivery. And we've implemented recently TLS as a special type of transport, and we'll get into more details a bit later. And the fourth component of the stack is VCL, VPP Communications Library. And the goal with this is we'd like applications to, well, we expect applications to want to link against it as opposed to directly linking against the session layer APIs, the raw session layer APIs, for reasons that have to do with asynchronous communication. So for instance, the session layer does not offer any EPOL implementation. VCL does. For those cases when you have legacy applications which you don't want to touch and you haven't statically linked them, we have an LD preload shim layer which can, well, intercepts your syscalls, injects them into VCL, and everything should work transparently. That effort, I expect it to be an ever ongoing effort just because of the number of communication combinations and difficulties, let's say, with building such a library. But it already works pretty well with some scenarios. So having gone through all of this, how do we tie it all together? How do we expect the stack to actually work? And let's take 3 separate examples. First of all, we'll go over stream communication, very briefly datagram communication, and afterwards redirects, and we'll see what that is. So normally we expect applications to request host stack service from VPP by just issuing an attach command. At the end of it, the session layer, once it receives it, allocates per application state. It allocates for this application a shared memory segment. Within the shared memory segment, it allocates some queues for notifications that have to be exchanged between the two. And once it finishes, it notifies the app of the success. Now, if the application is a server, it will probably issue a bind. Otherwise, if it's a client, it will issue a connect. So for a situation when the two of them, let's say, want TCP transport, how would this work? Well, in case of the server, the session layer, once it gets the bind, because the service requested is TCP, the session layer asks from the TCP layer to actually listen on whatever the transport endpoint was in this case. And in case of the client, at the end of the connect, the session layer asks the TCP layer to open a connection to whatever the transport endpoint was. In this case, the transport endpoint, the peer is the server. So the two of them do the typical TCP handshake, at the end of which, if this succeeds, the TCP, well, asynchronously, although here shows synchronously, TCP layer notifies the session layer of the success. The session layer allocates shared memory FIFOs that will be used for the communication, the TX and RX FIFOs. And the session layer finally notifies the applications in both cases. At the end of this transaction, the two of them, the client and the server, can exchange data. And let's say the client is sending some data here to the server. In this case, what it will do, it would push some data into the TX FIFO, sends a notification to the session layer reads the data, builds segments, packetizes the data, then asks the TCP layer to reliably send this data to the peer receives it, dequeues. Eventually, everything gets written to the RX FIFO, and a notification is sent to the server, and the server reads the data. And this continues until the communication ends. And to give you some very rough numbers about the performance you can expect, and I've run this very recently just to make sure that we're still doing fine. We're slowly onboarding this into SysIt as well. We're on a relatively modern server, E2699. We can do 12 gigabits per second per core with the 1.5 K MTU, actually 1460, and about 20, this is half duplex, and about 20 gigabits per second per core with a 9K MTU. Star in the margin here, we don't do PMTU discovery yet, so this was manually configured. And we can handle about 185,000 connections per second. For all this testing, what we've done, we've used the built-in within VPP Echo client and Echo server, and in this case, I think the server was dual core, but the client is dual core, but it's only capable of sending, it can only use one core to establish the connection. So it's actually not really dual core. What happens in case of datagrams? So how do we exchange data in case of datagrams? Well, the difference is that now the connect and the listen calls actually are synchronous in the sense that once they're issued, we already allocate the shared memory FIFOs within the shared memory segments. We don't wait for UDP to do any handshake because none happens. And instead of doing stream enqueuing into the FIFOs, what we do is we write data with a datagram header in the FIFOs. And the datagram header identifies the connection, the fourth tuple, because the protocol is already identified, and gives some information with respect to the size of the chunk that's being written and some additional details. And finally, the case of redirected connects, the one that I started with and said that it's not very efficient. So what happens when the client and the server are actually attached to the same VPP instance? Well, if the server does a bind and then the client does a connect, the session layer figures out by itself, like, right, the server and the client are local. In other words, they don't really need a transport layer protocol. They could just use shared memory FIFOS for the communication, and it just does that. Well, previously, and again, this is an update with respect to previous versions. Previously, because we used only shared memory segments that had file backings, we could just directly redirect and say, okay, you client and server applications, figure out how to allocate the shared memory FIFOs by yourselves and just do the transport. Since we use memfd, now we also support memfd shared memory segments, and because the client and the server do not have a binary API connection between the two of them that uses sockets, we actually have to allocate the segments within VPP. So VPP's session layer allocates a shared memory segment for this specific communication, allocates some FIFOs in it, some queues, and asks both the client and the server to map those shared memory segments, and then they can exchange the data. Now, in all the cases, this doesn't change at all. And transfer between the server and the client is just memory bandwidth constraints. So we can very easily do something like 120 to 128 gigabits per second. So it's pretty fast. Now, one thing we didn't touch upon is multi-threading and scaling of performance. And before I quickly go over what needs to happen in the stack, let's just take a step back and talk about what happens in VPP. Well, VPP is, as you well know, one of the main features of VPP is that it does vectorized packet processing or batched packet processing, which if you combine it then with the modeling of the forwarding as a directed graph of functions, or in case of VPP language, of nodes, now this results in a very efficient use of CPU instruction and data caches, and that makes VPP really fast. And we wanted to use this same, one of the benefits of this was one of the benefits of this approach, but the other one that's not very often mentioned is this can be scaled very well. So it's very easy to go from one core to multiple core, because you just need to copy the forwarding graph for multiple workers that you have running within VPP, and now use RSS hashing to distribute the flows over all these workers, so you make sure that you don't have reordering of packets within the flow. And because typically you don't need to do any sort of interlocking between the workers, because now flows are independent, they're running independently on their specific cores, you can scale performance linearly with the number of workers or cores that you're willing to offer for performance forwarding. We wanted to use the same sort of approach for the stack. However, you cannot do that always. You can typically do it for connection-oriented protocols like TCP, because then you can allocate per thread data structures for the session and the transport layer, TCP in this case. And except for the moments when you have to establish a connection, which it's a bit more difficult because you don't know exactly where the connection, on what thread the connection will end up on. Except for those moments, we typically run within VPP with connections pinned to a thread and with no locking. We don't need to do any sort of locking for accessing the data structures. So we've taken now the same principles, the vectorization from the IP layer up into the session layer for this sort of for connection-oriented protocols. And I mentioned when I give you a brief overview of the stack that the session layer has means to control the way applications can interact with the networking resources. And we have two of them. One of them is the namespaces. That is, whenever an application attaches to VPP, it has the option to provide a namespace it wants access to and it needs to provide the secret to actually gain access to that namespace. And namespaces are configured in advance by the management system, so this is a somewhat orthogonal problem. But what they do is they associate applications to networking resources, interfaces, and FIBs. Or in other words, they constrain the source IPs that an application can use, and they constrain the routing, the type of routing an application has access to. So if you want an application not to see the global FIB, it will see just a local FIB or a special design VRF for it. Well, you can do it via namespaces. Namespaces can share FIBs, so they can work on top of FIBs or routing tables. In which case, inter-namespace communication will happen with share memory FIFOs. If they don't share the FIB, so like FIB1 and FIB2 and namespace 1 and namespace 3 here, well, in that situation, if there's no form of VRF leaking between the two FIBs, communication cannot be established. And in a situation when there is VRF leaking, we cannot use share memory FIFOs because we have to go deep into the whole stack to actually establish the connection. And the other option the session layer has to control the way applications interact with the networking are the session tables, and in particular, the session rules tables that we have there. So when an application attaches, another option offered to it is to specify the sort of scope for its communication within the namespace it connects to. And we have two types of scopes. We have local scopes and global scopes, and actually an application can request both of them at the same time. The local scope means communication will always happen only through the session layer. It never requests service from the transport layer. In the global case, it requests service from the from the transport layer. And the interesting thing here is that, using this sort of separation, we can now build ACLs into the session layer. That is, we can use the local tables, the session layer local tables, to build egress ACLs. That is, whomever wants to connect to a remote peer, to a destination IP, now has to go through a special table that may filter or accept or reject a given connection. And in case of the global table, which is FIB specific, we may use the session rules table to let ingress communications pass or not, so accept them or drop them. And finally, one of the newest, well, the latest things that we've done within the stack, we've also implemented TLS as a transfer protocol. Now, as it turns out, TLS is an application layer protocol, actually. So what we've done within VPP is we've implemented an application that, when VPP starts up, presents itself as a transfer protocol. And if you've been counting, right now we have support in terms of transfer services within VPP for connection-oriented protocols, what I call, I guess, virtual circuits, connectionless protocols, and now application protocols. In other words, applications that just masquerade as transports. So in this sort of situation, when, say, for instance, that an application wants TLS service, it just goes to the session layer, asks for TLS transport. The session layer knows how to redirect this to the TLS app. The TLS app knows how to handle this. It allocates special state that it will manage for this connection, and afterwards it behaves like an application. It knows how to ask yet again the session layer for transport, and TLS wants as transport TCP in this case, so it knows how to build this. And finally, as you see here, we have two sets of FIFOs. So one for each application, for the external application, and one for the TLS application. And the TLS app knows how to join this two and actually make data flow from TCP up to the actual session. Very important note here. We didn't implement the actual protocol. Instead, we leverage OpenSSL and Embed TLS as libraries, well-known, well-tested. And we ingest them into VPP as plugins. Basically, the plugin code is just wrapper code that and we call those engines. Basically, the plugin code is just wrapper code that knows how to interact with the library, and then the TLS app knows how to work with these engines. If it's a server, it knows how to configure certificates. We have APIs for configuring certificates and keys. If we need to validate TLS connections, the CA authority, we build it reading etc SSL cert CA certificates. This is configurable. And we only support right now software acceleration, well, actually AES and I. We're working with Ping and Ray. Thank you, Ray, again, from Intel on accelerating this, accelerating OpenSSL in particular with QAT Intel cards. And to give you an idea of how fast this is, we managed to do something on the same server, on an E2699, something like 1 gigabit per second per core without any sort of hardware acceleration. And we're really CPU bound in this case. And because I've already been told that I'm out of time, ongoing work, well, this is a sort of a never-ending story. We're working on Envoy, on Kate's and Envoy integration on the VCL side. We're working with respect to TCP on several things, and the list is ever growing. We need on Policer, TSO, hopefully we'll manage to do it. New congestion control algorithms. PMTU discovery is another important thing that we'll eventually have to do. And well, there's lots of things that need to happen. For those of you who are interested in this, you have some pointers here. And the dev mailing list, VPP dev mailing list, is probably the best place to start conversation, or IRC. Thank you very much, and hopefully I'll have some questions. Go ahead.
If you want to pass it down, and then I can run around.
Thanks, Florin. Was there ever a temptation at any point to write a native TLS implementation in VPP itself?
I'm sorry to say that, yes.
But
yes.
that the temptation was overcome?
Yes. Well, it's a matter of maintaining this code, and it has a huge surface that
it's a non-trivial undertaking, right?
Yes, and well, on the one hand, it's quite complicated. On the other hand, this is a place that's typically under attack within the internet, and we would really need to spend constant time on handling this. And we decided that we don't have the manpower or the will at that time to undertake such an effort. So then again, we decided to use OpenSSL for this, and we realized that it works pretty well. For the ARM or embedded world, that's why we did Embed TLS, just to see, okay, how hard would it be to do a different type of OpenSSL SSL engine.
Can I beg one more question?
As long as nobody stops me.
Do you have any insight into how much time is being spent in Embed SSL, TLS or OpenSSL versus how much time is being spent in VPP in the benchmark cases you had?
That's a very good question. I don't remember off the top of my head. I can tell you only that we're CPU bound, so I won't be surprised if 50%.
It'd be an interesting number.
Yeah.
Thank you.
Fair point. Thank you.
All right. Any more questions? All right. We'll take one more question, and then we'll head on to the next presentation. So there.
We have a user case that if we use a TCP connection from client to the TCP server, and in the backend we have like running the NGX to load balance to a backend server. So the TCP have to terminate in a TCP server. How do you connect the client side and the backend server side TCP sessions? Reason is the backend side, when the packet coming back, RSS may route the packet into a different core. Is that handled by the local session table and global session table?
So let me see if I understand this correctly. You're running both of them on the same VPP instance?
The VPP instance can if I deploy to the multiple core, and one core can handle the client side of TCP session, and it terminate that.
Right. So let me see if I can clarify this. If they're running, if you're running both the server and the client on the same VPP, so they're attached to the same VPP instance, TCP is never hit. If you are running them on separate machines, RSS hashing ensures that a flow will always hit a given core. Apart from the moment, and the corner case here is when you open a connection. So for instance, when the client opens the connection, it does not know yet where on what thread the connection will end up. So what happens, that's the place where we do a bit of locking. We open the connection, we wait for the SYNAC to come, and once the SYNAC comes, we figure out the thread where we should be. We clone the connection to we instantiate the connection on the right thread, and from that point onward, the connection will never change threads. So I don't know if I answered with that your question.
Oh, that's one way to handle that. Thank you.
Okay.
All right, cool.
Thank you.
All right, cool. Thank you very much, Florin, for
Thank
your
you.
presentation. And thanks for questions.